Welcome back. This is Unit 3.3 on light, and this is pages 146 to 154 in your textbook and 64 through 68 in your study guide. All right, so we're going to be talking about light, and we're going to be doing a lot of calculations. This section of Unit 3 is heavy on math and calculations. So as we start out, we need to realize that properties of light has properties of a wave. So I know that you studied waves in junior high in probably the 8th grade, but we're going to talk about the parts of a wave again. So if you go ahead and draw this and label this in your notes, and you can pause the video to do that. All right, so wavelength. Wavelength, the definition of wavelength is the distance between two adjacent points on a wave. So what normally is done is you'll measure from the top of one wave to the top of the other, or from the bottom of the wave to the bottom of the other. But actually you could measure here where it hits the baseline. You would not go here because look, the wave's going down here. It's going up here. So you're going to have to go to the section of the wave where it's going down again. So that's why we measure between either the crests or the troughs, because if you measure on the baseline, it gets confusing. But we could also measure from here to here. So it's just any two points, adjacent points on the wave. And the symbol for wavelength is the Greek letter lambda. So it looks like this. So if you look at it really close, let me go ahead and erase all of the markings that I've made. If you look at it really close, it reminds me of a portion of the wave with a little line on it. See, because it goes up, and at the bottom it'll turn up, and then you have a little kickstand or something. So that's how I remember that that's the symbol for wavelength, because it kind of looks like a wave. Okay. And another part of the wave that's going to be important is called the amplitude. And that's the distance from the baseline to the top of the crest. And the amplitude is going to tell you, over here it shows you how bright or how dim that light is going to be. So the lower the amplitude, the dimmer the light. The higher the amplitude, the brighter the light. So the color of the light is not going to change, but the intensity, how bright or dim it is, will, depending on the amplitude of the wave. Okay, and then another concept that we're going to have to talk about when we talk about waves is frequency. So here we have 3 different blocks, and if you'll notice, these blocks are of the same length. Okay, so they are the same length. However, the number of waves from this point to the end point is different. So if we look at this one, we only have 2 waves here. Okay, and on this one, we've got 1, 2, 3, 4 waves in that same distance. And in this one, we've got 1, 2, 3, 4, 5 waves in that same distance. So this is called the frequency. How frequent do we have a wave in a given distance? Okay, and frequency determines the color of the wave. If we're talking about the visible color on the spectrum. If we're not talking about the visible spectrum, then we're talking about what kind of wave it is. And we're going to look at the electromagnetic wave spectrum here in just a second. So that's frequency. Frequency uses 2 different symbols. The original symbol is the Greek letter nu, which looks like a fancy V. So it's like this. Or you'll see it as written as a lowercase f as well. So either one of those, like in your notes, in the reading, in the textbook, or maybe some problems that you may see written by different people, frequency is used 2 different ways. All right. So if we look at the electromagnetic spectrum, and I don't expect you to draw this, I'm going to give you a handout that has this on it so that you can look on it. But the electromagnetic spectrum goes all the way from the lowest energy or the longest wavelength, radio waves, all the way up to gamma rays, which is the highest energy and the shortest wavelength. So the lowest energy and the longest wavelength is going to be your radio waves, and then come your microwaves, and then infrared. And then in this very small area right here between infrared and ultraviolet is the part of the wave that we can see with our eyeballs. Then it's ultraviolet, X-ray, and then of course the highest energy, the most damaging, is the gamma rays. And so if we look just at this area right here, visible light, we can see that the lowest energy of light is going to be red. So it goes red, orange, yellow, green, blue, indigo is right in this area, indigo, and then violet. So you can remember the order of the spectrum by remembering a person's name, and it's Roy G. Biv. Okay, red, orange, yellow, green, blue, indigo, and violet. So intuitively, you always think about the color red being high intensity because, we're told that, if you want to make a bull angry, the matadors use a red cape. So we always think about red being high intensity. Red is the lowest energy color, where purple is the highest energy color. All right, so if we look at white light, so all of the colors together here in the electromagnetic spectrum, the visible light section, that's called white light. So we see light that comes from light bulbs or the sun as defined as white light. So if we pass this white light through a prism, which is a triangular piece of glass, then it splits it up into different wavelengths. And we can see those wavelengths as a rainbow. And sometimes the droplets of rain that are still suspended in the air do this, and that's how we see a rainbow. Well, different elements have what's called a different emission spectrum. And we're going to be looking at this in a lab that we're going to be doing. So say, for example, if we take hydrogen and we pass the light, if we concentrate it down, this section is here, just a slit. We concentrate that down into a slit and then run it through a prism and break up the light that's in hydrogen. We can see it leaves a very distinct what's called spectrum or fingerprint. So hydrogen leaves these 4 color bands on this black background. So this is called the emission spectra or the fingerprint for hydrogen. And each element has their own spectrum. So we see here in this example, helium has 6 bands at these particular wavelengths of light. And then barium, another element, has a different spectrum. Some of these spectrums can leave, these elements can leave a lot of bands on them. So this is how scientists analyze the light that comes from a star or from another planet, and we can tell what the atmosphere or what the star is made of, what elements, because they compare these to the spectrums. And this is also how Niels Bohr came up with the planetary model of the atom, where it's different rings, because he saw that these rings here corresponded to electrons that are in different energy levels. Okay, so we have here 2 more spectrum, and this is, instead of being on a black background, it's on a continuous spectrum background. Like this is white light right here. So white light run through a spectrum. It looks like a rainbow. We see the continuous spectrum or continuous colors. So this is on a continuous background. But if we look at oxygen and neon, we can also see how many bands there are. All of these bands that appear. And these are much different than neon. That's why they're called a fingerprint, because everybody has a different fingerprint. People are identified by their fingerprints. Same thing with elements. Each element emits light in a different pattern on the spectrum. All right, so going on, if we look at how light is emitted from these elements, we're going to use the Bohr model. And so what happens is these electrons that are in these orbitals can absorb energy, and they absorb energy either from UV light, or they can absorb energy from heat. So when these electrons absorb any kind of energy, they're going to start spinning faster around the nucleus. And when they do that, then that's going to do is it's going to cause them to jump into a higher orbital. Just like if it was a satellite going around the Earth, if the speed of the satellite increased, then the radius of the orbit is going to also increase. So if we put energy into an electron, it's going to jump, like say, for example, this one, it's going to jump from this energy level up to this energy level. But it doesn't stay there forever, because once that electron loses that energy that we put into it, then it's going to fall back down to its original orbital. Okay, and its original orbital is called the ground state. The ground state. So you need to remember that. The original orbital of an electron is called the ground state. Well, when it falls from the higher energy level to its ground state, what happens is it emits a photon of light. Okay, and in a certain wavelength, and we see that as light, a color of light. So remember back here on the spectrum when I said that red is the lowest energy. So if an electron jumps to an orbital and releases a small amount of energy, we may detect that as a red color. But if it absorbs enough energy to bump it up 2 orbitals, when it falls back down, it's going to release more energy. And we may detect that as a blue-green. And going along with that, if it releases a large amount of energy, then we're going to see that as a more purple. So if we look back at the continuous spectrum, this is flipped from what this is. See, red is on the left-hand side here, but on this one, it's on the right-hand side. That doesn't mean that it's flipped energy. That just means they took and turned it over and are looking at it from a different direction. But if we look at it on the electromagnetic spectrum that corresponds to energies, red is going to be low energy, where purple is going to be high energy. So the higher energy, the more towards the purple end it's going to be. The lower energy, more towards the red end. Okay, we're going to use this concept in our next lab that we're going to do. We're going to heat up some chemicals using a Bunsen burner, and these chemicals are going to emit certain colors of light, and we are going to record that and then identify some unknowns maybe that we have as to what the possibilities of the chemicals that are in the unknown. Okay, so that's a fun lab. Now, the practical application of this is neon signs. So when you take and run electricity through gas, these electrons are going to absorb energy and release energy. And when they release energy, it releases light. So they take these glass tubes and they fill it, they pump in compressed neon, and then they'll seal the tube off with a wire in there, and they'll run high voltage electricity through this. And when they do that, it makes the gas glow a certain color. So if you're in the classroom and you're sitting in the classroom and you look up at the fluorescent lights that are above your head, those are just a glass tube It's a glass tube like this. And you may have seen fluorescent lights if you have these at home. It's a glass tube that has a metal seal on each end. And that metal seal on each end holds two little probes that stick out on each end. And then so you put these up into the mechanism, and it runs electricity through here. And as it runs electricity through there, the gas that's in these tubes will emit light. And if you've ever taken a fluorescent tube like this and broken it, when it breaks, it kind of explodes. It has this big popping sound because the gas inside here is being compressed in the fluorescent light. All right, so as I mentioned earlier, we do have a lot of calculations that we're going to be doing with this section. And so some of the constants that you're going to need are the speed of light and Planck's constant. And here are some of the equations. So pause, please, and write this down. So the speed of light, the equation for the speed of light is the wavelength times the frequency of the light. And you can find these constants, and you can find these formulas in your formula chart that you have in the front of your notebook. So wavelength times frequency. So if we're looking at this as symbols, it's going to be wavelength times frequency. And I'm just going to use an F for frequency. So wavelength times frequency is going to be the speed of light. And you can also rearrange this. So if we're asked to calculate the wavelength of light, then you may have to rearrange this so that you are calculating the wavelength, because the speed of light is a constant. Okay, and C is the symbol used for the speed of light. So we see here, C is the speed of light, and the value for that is 3.0 times 10 to the 8th meters per second. Energy is the speed of light, which is C, times Planck's constant. Planck's constant is a constant number. It never changes. It's 6.626 times 10 to the negative 34th joules times seconds. So joules seconds. And that's divided by wavelength, which is the lambda. And frequency has a unit, and this is the unit for frequency. Frequency is commonly given to you in a word called hertz, but there is a numerical or mathematical value for that, and it's s to the negative 1 power, or if we change that into a fraction, that's going to be 1 over s. So make sure you have these written down. All right, and pause here and write down the units for these. All right, so the units for wavelength are going to be given to you in nanometers. So I'm going to go back here to the electromagnetic spectrum that's given to you. Okay, and here, right here, the wavelength is given to you in nanometers. Okay, so when you're given a wavelength of light, you're going to have to convert that to meters, because the speed of light, the constant 3.0, is given to you in meters. So in order to use these in a calculation, we had to make sure that the units are the same. We can't have a calculation where in one variable we use nanometers and the other we use meters. They have to be the same. Frequency, hertz, like I said, that's s to the negative 1 or 1 over s. The speed of light is given to you in meters per second. So if we use abbreviations, it's going to be meters per second. And then Planck's constant is joules seconds, or joules times seconds. All right, so it's going to be very important that you brush up on your Algebra 1 and you know how to rearrange and cancel, because this is going to be a unit where we're going to have to do a lot of that, a lot of heavy calculations. So the first calculation example that I want to do for you is converting a wavelength of light into meters so that we can use it in our other formulas. So we're going to take, let's say, for example, we're given the wavelength of light is 656 nanometers. We're going to have to convert that to meters. So we're going to take our nanometers and put it over 1. Okay, and then we're going to follow those steps that I've taught you on doing a conversion. So what unit is it that we want to get rid of? The answer to that is nanometers. So where do I put it? In the bottom, because that's what I want to get rid of. All right, so now we're going to have to convert it to meters. All right, so I'm going to look at my conversion factor that I have here. Now remember, conversion factors are equalities. It's one thing that equals another. So we see here that we have 1 meter is equal to 1 times 10 to the 9th nanometers. This is not a number that you're going to have to memorize, but you're going to use this so much that you will memorize it. But if you do forget it, like you are taking a test and you have test anxiety and you just can't remember it, that's going to be given to you anyway. So don't worry about that. So 1 meter is equal to 1 times 10 to the 9th nanometers. Okay. All right. So when we get our calculator and we do this calculation, we're going to see 656 divided by 1 times 10 to the 9th meters is going to be 6.56 times 10 to the negative 7th meters. Okay. Why meters? Because nanometers cancels out. We forced canceled that. Now, in these calculations, we're going to have a lot. Most of our answers are going to be in scientific notation because we're dealing with very, very short frequencies because we're dealing with light. We actually can't see any of these frequencies, the actual wave, because it's so small we can't detect that with our eye. We just detect the color. So lots of scientific notation in this section. All right. All right, so a typical problem that you're going to be seeing is this. So go ahead and write this down, and then I'm going to work it out together, and you're going to pause and you're going to write all this down as an example in your notes. All right, so it says a bright line spectrum contains a line with a wavelength at 518 nanometers. All right, so that's all we have. That's our given, so I'm going to circle it. Now, every time I do a problem, I always use glues. So you should probably get used to doing that because that's going to only help you in the future. All right, so our first question here, the wavelength in meters. So we need to calculate this wavelength in meters. All right, so let me gather my notes here. So we're going to have to change this nanometers right here into meters. And this is the exact same calculation that I did here. All right, so I'm going to take this 518 nanometers. I'm going to put it over 1. I want to get rid of nanometers, so I'm going to put that in the bottom. I'm going to convert it to meters, so I'm going to put that in the top. 1 meter is 1 times 10 to the 9th nanometers. My nanometers is going to force cancel. Okay. And then when I calculate this, I'm going to get 5.18 times 10 to the negative 7th meters. That's my answer there. Okay. So I'm going to go ahead and make note of this because I am going to erase so I can do the other ones. Okay, so I'm just going to leave that there because we're going to need that in just a minute for other calculations. Okay, so the second question is calculate the frequency. Well, if I look back at both of my equations that I have here, I see that the speed of light is wavelength times frequency. And I see here energy is Planck's constant times the speed of light divided by wavelength. So if I'm calculating wavelength, I don't have energy. So I'm going to have to use speed of light. So if the speed of light is equal to wavelength times frequency. All right, so if I have this equation and I'm solving for frequency, I have to rearrange this equation so I have frequency by itself. So I'm going to divide both sides by the wavelength. When I do that, wavelength cancels and it leaves frequency is equal to the speed of light divided by the wavelength. Okay, so if this is the wavelength here in meters, I'm going to use this calculation along with the speed of light. So the speed of light is 3.0 times 10 to the 8th meters per second. And that's all divided by the wavelength, which is 5.18 times 10 to the negative 7th meters. Now I'm going to just work with my units first and get my units all taken care of. So if I look at just my units, I have meters over seconds divided by meters. If we make that a fraction like this one, it's going to be meters over 1. Now, if you think back to your algebra, the way that we divide fractions is I don't remember what I heard a couple of weeks ago, keep, flip, and multiply or something like that. But I remember it as you multiply it by the inverse. So I'm going to keep meters per second and I'm going to multiply by the inverse of the denominator. So that's going to be 1 over meters as an inverse. Now, meters cancels meters. So what I'm left with is 1 over seconds. Okay, and if we look back, we can, at your notes that you wrote down for hertz, hertz is 1 over seconds. Okay, so we're going to get our frequency in hertz, which is abbreviated Hz. So now that I know all my units work out correctly, and I know I'm on the right track, and I can just go ahead and now do my math. Okay, so if we clean this up just a little bit and get all the units out of the way, because I know that the units are correct. I worked out the units. Okay, if I get all this out of the way so I can just see the numbers, then I know that for the numbers, it's just simply 3.0 times 10 to the 8th divided by 5.18 times 10 to the negative 7. Okay, so pick up my calculator. 3.0 times 10 to the 8th power divided by 5.18 times 10 to the negative 7th power. That's going to give me 5.79 times 10 to the 14th 1 over seconds or hertz. And you see, I'm keeping all these calculations that I have because these are now part of the facts, part of the known calculations, because I might have to use this now in a different formula. Right, so calculate the energy. So the formula for energy is E is equal to Planck's constant, you hear my dog whining, times the speed of light over the wavelength. We're going to multiply this by the speed of light, which is 3.0 times 10 to the 8th meters per seconds. Okay, and then we're going to divide all of this by the wavelength that we calculated. So that's going to be 5.18 times 10 to the negative 7th meters. Okay, so this is some pretty complicated algebra to get all of these units situated. So let's look at it. So we have joules times seconds times meters over seconds divided by meters over 1. Okay, so if I do this just like I did the last problem, where I take joules times seconds times meters over seconds, inverse and multiply 1 over meters. And let's look at what I have and what I can cancel. All right, so we have seconds on top and seconds on bottom. That can cancel. We have meters on top and meters on bottom. That can cancel. Here's a 1, so we have joules times 1, which is what's left. So joules times 1. Anything times 1 is itself. So we have joules over. We cross both of these out, so that makes that a 1. Okay, so joules over 1 is just joules. All right, so that is the frequency for energy. Energy is in joules, and it's called Joules. Okay, Joules. So now that I know I have the correct unit for energy, then I know I've set this up correctly. So I can just go ahead and multiply the numbers now. I don't have to worry about the units because I've already fixed the units. So I'm going to go ahead and subtract or erase out these units. And then I can just worry about the math. So if I take all of this other stuff out so I can clean this up, I see that the math here is Planck's constant times the speed of light divided by the wavelength that I calculated in A. All right, so if I grab my calculator, 6.626 times 10 to the negative 34 times 3.0 times 10 to the 8 divided by 5.18 times 10 to the negative 7th. Going to get 3.87. Let's see, I'll write it right here. 3.87. And these are all 3 sig figs, I'm sorry, because our original data is 3 sig figs. 3.84. I made a mistake there. Because it's 3.837. I was looking at the 7 for rounding and I said 7. I meant 4. 3.84 times 10 to the negative 19th joules. Oops. That's a 19. Let me just erase that just so I can be sure I make it very clear. 19 joules. Okay, so that's the answer on that. All right, so this next question is asking, what is the color of this line? Well, when you have a question that asks the color, you're going to have to look at the nanometers, the wavelength of the nanometers, because that's how it's given on the spectrum. So it's just going back to our original data in our problem. So it's 518 nanometers. So if we come back over here to the spectrum, 518 nanometers. So let me erase this line. Okay. It's going to be, let's see, this goes from 500 to 550. So 518. So if this right between there is 25, because halfway between 500 and 550 is 25. So 18 is going to be somewhere around in this area right here. So we're going to say it's going to be a green-blue line because it's just on the edge of blue. Okay, so green-blue. Green-blue. Okay, so those are the calculations. Thanks for watching. Make sure that you slap that like button right across the face, and make sure you click subscribe and the bell so you can be notified of when I put up new videos.